Hi, my name is Daniele Di Sarli. I am a PhD student at the Department of Computer Science at University of Pisa, where I am studying efficient recurrent machine learning models. So let's get started with the presentation. The name of the work is Federated Reservoir Computing Neural Networks by Davide Bacciu, Puria Faraji, Claudio Gallicchio, Alessio Micheli, and me. The work deals with federated learning of machine learning models. So we can imagine a scenario like this one. We have a number of edge devices, which are represented here as vehicles. And these devices have access to data which is available locally. Okay, so the goal is to produce centrally in a server a central model which encodes knowledge from all this data. And a way to do that is just to collect the data locally on the edge devices and then send it to the remote server. But of course, this has issues. The first one is a privacy issue, because if you are dealing, for example, with sensitive data, you cannot just take it and ship it to a remote server, which is not controlled by the user. And then we also have bandwidth issues, since the central server is remote with respect to the position of the edge device, and the data may be big. Think, for example, at data produced by sensors. So we cannot afford to send this data to a remote location. And this scenario is part of what the teaching project is doing. So teaching is a research project funded by the European Union, and the name stands for a computing toolkit for building efficient autonomous applications leveraging humanistic intelligence. So in short, the teaching project deals with cyber physical systems of systems, which are around us and will be more and more around us in the coming years. And the observation is that the human is a critical part of these systems. So as such, it deserves special considerations in this kind of applications. So the goal of teaching is to design a computing platform and a software toolkit for the development and for the deployment of autonomous, adaptive, and dependable applications for cyber physical systems of systems. So allowing these applications to exploit human feedback to optimize and personalize the services that are offered. The results that we will present today are part of the research for the AI as a Service toolkit, which is part of teaching. And if you want to find more about teaching, you can follow the URL at the bottom of the slides or the social channels on LinkedIn and Twitter. So let's get back to the problem of federated learning. A trivial strategy that actually works is to send to the server not the data, but some models trained on the locally available data. So, for example, here we have some edge devices, each of which trains a machine learning model with the data that is available locally, producing some weight matrices. And this is done separately for each edge device. And then the matrices are shipped to the server, which performs a weighted average for each of these matrices. So, for example, say that these matrices are coming from a long short-term memory model. We take all the matrices, all the weight matrices corresponding to a given part of the architecture, for example, the F matrix, and to compute the aggregated F matrix, the server computes a weighted average of the F matrices of all the clients, and the same for the other matrices. We can do that with basically any kind of models. But in particular, we are interested in recurrent models. And an instance of recurrent models is provided by Reservoir Computing and ecostate networks. Ecostate networks are a particular kind of recurrent machine learning model, neural network models, which is structured like this. We have a recurrent part, which is called the reservoir, which is a dynamical system that produces a state at each time step. And then we have a linear readout, which takes the state of the reservoir and produces a prediction. Now, the key characteristics of this approach is that the weight matrices inside the reservoir are fixed. So they are initialized based on some mathematical properties, and then they are not trained. And you see here at the bottom the equation describing the dynamics of the state inside the reservoir. Then the training happens just within the readouts. So the readout is a linear layer. It has a single weight matrix, takes the state of the reservoir at empty and produces an output Y. So since the training is limited to the readouts, ecosystem networks provide a very efficient approach for modeling sequences. And the training also is peculiar because since we need to only train the readouts, which is linear and is like this, we can afford to do it in a different way with respect to what is commonly done with gradient descent. So instead of gradient descent, we use retrogression and we compute the weights of the readout like this. So we have the targets in the matrix Y. S represents the states collected from the reservoir, and by computing this result, we obtain the weights for the readout. Now, the same averaging strategy for federated learning that we have seen at the beginning can, of course, also be applied to ecosystem networks. So the edge device here computes a matrix. Here the subscript indicates the client C using retrogression. Okay, and in the server, what we do is we compute the aggregated weight matrix by a weighted average of the weight matrices of all the clients. This is a straightforward approach, but there are not many guarantees on the results of this aggregation. So here comes our proposal. So we can exploit the decomposition of the training equation. So this is the same equation that we have seen before for client C to compute the weights of the readouts. And we can decompose it like this. We call the first part A and the second part without the inversion B. And notice that these matrices do not depend on the number of training data. In fact, they only depend on the shape of the output and of the reservoir. And at this point, we can send the matrices A and B to the server, which can compute the final equation by multiplying A with the inverse of B. And this produces the weights of the model, which are in the readout. Now, A and B are just the sum of the A matrices and of the B matrices of all clients. This method gives some advantages or guarantees. So the first one is that it allows optimal aggregation. What does it mean? This means that our decomposition is mathematically equivalent to a hypothetical centralized model trained on the whole training data from all the devices. Okay, it is as if the training data were directly transmitted to the server, but they are not. Another advantage is that of privacy preservation. So since no data is shared, you do not have to worry about leaking sensitive information. And in fact, the server only sees the matrices A and B of each client, which, however, do not allow to reconstruct the training data. For example, data coming from sensors. So the original training data cannot be recovered. A third advantage is given by the incremental computation of these matrices. So the idea that you can compute these A matrices and B matrices incrementally. And this is important because it avoids the need to store huge amounts of training data, which is especially important in edge devices which could be low power. To see what this means simply that to compute the A, you do not have to do it all at once, but you can do it incrementally. So as new data arrives, you compute a new matrix A with the data that you have, and you sum it with the A matrices that you had computed before to produce a new one. And since A does not depend on the number of training examples, the memory usage remains low. So we have performed some experiments to test this proposed federated learning approach. And to do these experiments, we have chosen a couple of human-centric datasets. So the first one is WIZET. It is a dataset containing biometric measurements of 15 subjects. The task is the prediction of the activity of the subjects, which are either baseline, stress, amusement, or meditation. And the second dataset is the HAR, in which there are 9 subjects, and the activities to predict are biking, sitting, standing, and so on. And as models, we have chosen to test recurrent neural network models, and we have compared the LSTM with the EcoState network. Here are the results. On the rows, you can see the number of training subjects that we have used for the experiments. And then on the columns, we have the different models. For example, this column represents the long short-term memory using the federated averaging approach. Then we have a centralized EcoState network that we use for reference, where all the data is available locally. We have another EcoState network which also uses the same federated averaging approach used by the long short-term memory. And finally, we have an EcoState network that uses the methods that we propose, which is that of incremental federated learning. Now, first, you can observe that for both datasets, as expected, the accuracy on the test set improves as the number of training subjects is increased, and this is expected. But what is interesting is, for example, let's take the last row. We can see that the incremental federated learning method produces an accuracy which is identical to the one of the centralized EcoState network. And this is also expected since they are mathematically equivalent. Moreover, the incremental federated learning produces an accuracy which is higher, better than the federated averaging methodology. And finally, all EcoState network approaches improve against long short-term memory aggregated through federated averaging. To conclude, we have shown that EcoState networks support a form of federation which is optimal, in the sense that this is equivalent to training a model with all the data available locally. This is great, for example, for learning on low-power edge devices, since by themselves, EcoState networks are great for efficiency. And with this federation method, we can also push a bit more on the predictive accuracy. And finally, notice that this approach is not limited to EcoState networks, but it is extendable to any model which exploits a training algorithm similar to ridge regression. My contact information is at the bottom of the slide. If you have any question, I'll be glad to answer. Thank you.